configuration for atoms. All right, very good. So we can write it this way. We can write it. I want you, by the way, did you sit down and memorize how the structure is done? Hello?
Yes, doctor.
Yes, Dr. Okay.
Must memorize this structure extremely well, extremely well. Either you draw it or you memorize it by one itself. And now I can do it in many ways. I can do it either I write it like energy levels, like I can say this is 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then 4p, and so on and so forth. So it is the same thing, but I wrote it here as energy level. This is energy, and this is the lowest energy. 1s is the lowest energy, and as you go up, the energy become higher and higher and higher. All right? Or I can simply write it like a structure, like 1s2, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. All of these things are giving the same result. Whenever you look at this one or this one or this one, I can also do it as boxes like this. Okay, and this is 1s, 2s, 2p, 3s, 3p, 4s, 4p. Right? Is this clear? Hello? Is this clear? Hello?
Yes, doctor.
Yes.
Very good. Now, now, after that, I want you also to know if I give you any element, like for example, sodium, then go and look at your periodic table. At your periodic table, what's the atomic number of sodium?
11.
11. So what will be the structure of sodium? I will do it this way just to make it simple. It should be 1s2, 2s2, 2p what?
6.
2p6, and then
3s1.
3s1, and that's it. Is this clear? All right, is this clear?
Yes.
Very good. That's one thing. Well, how about let's try something else. Let's try iron. Go and look at your periodic table and tell
26.
me what's the number of iron.
26.
20 what?
6.
26, exactly. All right, then what's the structure? Tell me what's the structure.
1s2. 2s2. 2p6. 3s2.
3p6, 3s2. Yes.
3p6.
3b6.
3p6, 4s2, 3d.
D.
What?
6.
6 only.
6.
What's left is 6, exactly. I can put up to 10, but I have only 6. Is this clear?
Yes.
Very good. I hope you can draw these things. Next, what I want you to know from this table also, how to find what are the numbers, the atomic, quantum numbers, which is N, L, ML, and MS. If I put any electron anywhere, let me put electron here. So if there is electron in 4s1, which is here, what is the value for N for this electron?
4.
Exactly. The number, the first number we write here is the number for N, which is 4. What's the value for L?
0.
Why 0? Fantastic. Why
S.
0?
Yes.
Because it is S, exactly. Because it is S, this means it is 0. Very good. How about ML?
0.
It must be 0 because you have no choice. There's only one value. How about MS?
Half or minus half.
Positive half.
Let's put positive half this time. Okay, so we agree that the thing at the top is positive half. Is this clear?
Doctor,
How do you know, Dr. MS? From where?
What again?
MS, from where you got this half?
As I said, MS has only two values, either plus half or minus half. We agree that we'll agree now that the arrow at the top to the top means plus half. Let's agree this, no problem. You have no choice for MS except two values, either plus half or minus half, only two values. All right, so we can agree, we can put this one up and this one down, or I can say no, I don't want this, I want to reverse it. No problem, because it's the same thing and it's the same energy.
Doctor.
This one is down and this one is up.
Doctor.
Yes.
Sure, but I don't understand exactly how can we know it's the MS when be positive and when be negative.
No problem. You can choose. You decide if the arrow is up. Do you want this to be half or minus half? You decide.
Okay.
What do you think? What do you want this one to be?
Like positive.
Plus half?
Yes.
Then automatically, what's this? You don't have to think now. This must be minus half. Clear?
Clear.
You decide. No problem. Or if I tell you that this one, now let's assume that I said this one, this electron, we're talking about this electron, okay? And I put MS as minus half now, okay? If I put electron here, then again, what's the value? I'm talking about this electron now. What's the value for N?
4.
4. It's not 4. Always the first number here is the value for N. Okay, what's the value for L?
1.
Fantastic. Why 1?
Since
P.
it's P.
It's a P, exactly. Fantastic. What's the value for ML?
3.
Minus 1 or 0 or 1.
Exactly. The value is minus 1 or 0 or 1. All right? Now, which one you choose? It's okay
Minus
to choose
1.
anyone. Let's assume that I chose 0. Okay. Now, what's the value for MS? Now, don't forget, look at this structure. We decide that MS here is what? Minus half. Clear? So what's the value for MS for this one? I must say
Minus half.
why? Because I decided that this electron, which is up, is minus half. So anything like it, it will be minus half. Is this clear? I hope so. Very good. Now,
Doctor,
yes,
how can I know if it is up or down?
you decide. As I said, it doesn't matter.
I know I decide if it's positive up or negative down. But I decide how I know if it's up or down.
Yeah. But as I said, you don't know. I mean, now I will show it to you. For example, now, again, let's say that we decided that what's the value for ml for this one, for this value here. We decided that this is 0, right? Good. Now, if I put electron or I draw the electrons like this here, what's the value for n? Come on.
4.
It is 4.
What's the value for L?
1.
What's the value for ml? Can I say 0?
Yes.
No,
No, I cannot say 0.
because I
used it. So what can I say?
1 or
1
minus.
or minus 1.
Yes, minus 1 or 1 minus 1. It's okay. It's up to you to choose. Let's say which one you want to choose.
1.
Minus 1.
Minus 1. Very good. Then this is minus 1. Then automatically, what's this?
Plus 4.
Clear? Now, what's the value for ms?
If it is it's plus half.
Plus half or minus half? It must be plus half because I decided that this one is minus half. So this must be plus half. Is this clear?
Yes.
Yes, please.
Fantastic. Fantastic. Good, 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 good. Now, let's assume that I have this electron. Then what's the value for n? 4 for L, 1 for ml. What's ml?
minus 101.
No, minus 1 only. I decided already. Minus 1. This one is minus 1, so this one must be minus 1. It's in the same room. And what's the value for ms?
Minus half.
Minus
Plus
half.
Positive half.
Because I already decided the one which is down is plus half, the one which is up is plus half. Is this clear? Now, look at these two electrons. What's the difference between them in quantum numbers? Only the last one is different than the last one, right? This is Pauli exclusion principle. You remember Pauli exclusion principle? Pauli. What does Pauli says?
the maximum number of electrons is 2.
2. There is another way to say Pauli exclusion principle. No two electrons in the same atom can have the same 4 quantum number. Quantum number. That's the way to say Pauli exclusion principle. Repeat it. Pauli exclusion principle. No two electrons in the same atom can have the same 4 quantum numbers. That's the same meaning like 2 electrons in an orbital. If you have 2, maximum you can have 2 electrons. If you put any other electron like this one, can you put another electron like this? No, you cannot, because in the same orbital, right?
Yes.
So you cannot do this. So you should have only 2 electrons like this, and these 2 electrons have the same N, the same L, The same ml, what's the difference? MS only. And that's why it says Pauli exclusion principle. We can say it another way. How? No two electrons in the same atom can have the same 4 quantum number. Is this clear? Very good. Okay, now another thing that I want you to learn also. Done with these things. If we want to draw the structure of if I want to know, by the way, before I go to this, I want to tell you that the structure that we're drawing, like this structure for Fe and this structure for sodium, these are called ground state. Ground state. What do you mean by ground state? This is, what is the meaning of ground state?
N equal to 1.
No, the lowest energy. What's the structure of sodium? 1 is 2, 2 is 2, 2p6, 3 is 1. That is the ground state. What do you mean by ground state? That's the lowest energy for sodium.
When n equal to 1?
What again?
When n equal to 1?
No. Ground state is the whole structure. This structure is called the ground state for sodium. Ground state for sodium. Is this clear? Ground state for sodium. I hope it's clear. Now, can I have the structure for sodium? Ground state means I mean by low state, when you draw the structure, which we just did, 1 is 2, 2 is 2, 2p6, 3 is 1, this is the ground state, lowest energy state. Can I have the structure for sodium? 1 is 2, 2 is 2, 2p6, 4 is 1. This means I take this electron from here and make it jump to 4s. Is this possible? It is possible, but this is not the ground state. This is one of the excited states. Excited معناتها مثارة, and ground means lowest energy. Clear? Clear?
Yes.
I hope this is clear. Why I'm saying this? Let's have the structure for, now I want to take this away. Everybody knows this. Okay, let's do the structure for nitrogen. What's the structure for nitrogen? What's the atomic number of nitrogen?
7.
7, exactly. What's the structure?
1 is 2, 2 is 2.
1 is 2, 2 is 2, 2p.
4.
3, 4.
3. No, 3. Okay, now let's put the electrons here. Again, what's this state is called?
Lowest energy.
Ground state or lowest energy. Ground state or lowest energy. Very good. Let's do the electrons here. There's 1, 2, 3, 4, and then where should I put the electrons? 5, yes, 6, and then 7, according to which rule?
Hans.
Hans, exactly. Hans rule. Don't forget Hans rule. You have to memorize this. Hans rule. And we put the electrons like so. I hope it's clear. Now, if I make the electrons like this. Is this correct?
No.
No.
Why not?
It didn't
Why not?
maximize
Because it's not according to Hans rule, right? Hans rule is only for the ground state, but this one is one of the excited states. So it is correct, but it is in the excited state. Is this clear? Is this clear? All right.
Yes.
Let's do something
Yes.
else. Let's do something else. I'm still drawing the structure of nitrogen. Is this correct? Structure for nitrogen.
Yes, but it's excited.
Yes, it is correct, but it is excited state. Very good. Okay. Still, I'll do one more thing. Let's take this away. And let's do it this way. Is this okay?
No. No.
Why not?
We can't.
Excited state.
We cannot have them. They must withdraw, do in different direction according to which law?
Pauli.
Pauli exclusion principle. Then they will have the same 4 quantum numbers, which is not allowed. The same 4 quantum numbers. So this is a wrong structure. Is this clear? Is this clear? I hope all of these things are very clear and things. Okay. I hope this is clear. Is this clear? Good.
Yes, yes.
Did you memorize the structure? I want you to memorize it extremely well. Now, let's go and solve this problem. Okay, calcium. 20. Okay, tell me what's the structure quickly.
1 is 2.
1 is 2. 2 is 2.
2b6.
6.
3 is 2.
3 is 2.
3b6.
3d6.
3p6.
4 is 2.
4 is 2.
4 is 2. Exactly. 4 is 2. And again, this is the ground state. This is the ground state or lowest energy state. I hope this is clear. And as I said, I can draw it this way. I can draw it this way. What else? Can I draw it another way? 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, 4 is 2. 1 is 2, 2 is 2, 2p6, 3p6. Can I do it another way? Yes, I can do the boxes in their energy level. So I can write 1s, 2s, 2p, 3s, 3p, 4s2. Is this clear? I hope so. Good. I want you to notice the following. Look at the periodic table. You have the periodic table in front of you. I want you to count. By the way, what's the maximum number of electrons you can put in S? Maximum number.
2.
2.
B.
6.
How about D?
10.
10.
10. Exactly. How about F?
14.
14.
Okay. Remember this very well. Now, I want you to count how many columns, forget about hydrogen, how many columns you have here?
19.
How many columns? Columns. عمود.
2.
7.
1, 2. 1, 2. Okay. How about this one? How many columns you have from here to here? Count them.
6.
6. So count them. 1, 2, 3, 4, 5, and 6. Okay. How many columns we have from SC to zinc? Count them.
8.
No.
10.
4, 5, 6,
10.
7, 8, 9, and 10. Okay. Now, how many columns do we have in here in lanthanides? Count them from here, from lanthanum to this one. Count them.
14.
1, 2, 3,
14.
4, 5, 6, 7,
14.
8, 9, 10, 11, 12, 13, 14. Good. Is there any relation between the periodic table and the S and P and D and F?
Yes.
Very clear, right? Good. All right. You will find
Yes.
that the alkali elements will always end up with S1. And what's the structure for the last orbital for lithium? What is it? The last orbital?
S1.
No, it will be 2s1. For lithium, it will be 2s1. Okay? For sodium, what is it going to be?
3s1.
Exactly. For potassium,
4s1.
okay, for rubidium.
5s1.
5 is
So
1.
you can tell what will be the structure without. So if I want to count, if this is 2, 3, 4, this is 5, and then I can tell what will be the last orbital for francium. 7s1. Clear? Good. How about for alkaline earth? To be always last orbital will be what? S
2.
S2.
2, S2, and it will be, you start from S2. So if you want the last orbital in strontium, this is 2, 3, 4, and it will be 5 S2 for strontium. Clear? I can tell from the structure. How about for this column, boron? What's the last orbital?
Two B1.
It will be the last orbitals. 2 S2, 2p1, 2p1, exactly. All right, and then if you go to TL here, what will be the last orbital? For TL, you have to count only, this is 2, 3, 4, 5, 2, 3, 4, and 5. And this one will be, last orbital will be 6, is 2, 6, P1. See, the last orbitals available for selenium. Okay, how about for oxygen? What will be the last orbital?
Two is 2, 4 6.
So for oxygen, 2s2, 2p4, 2p4. All right, and I will give you also a help from now on. The first column, which is this one, this is 1, and this is 2, and this is 3, and this is 4, and this is 5, 5. And this is 6, 7, and 8. Okay, the total number of electrons in the last SMP and these things are called valence electron. Valence electron. I want to memorize the word valence. And as I said, what's it for oxygen? It is 2s2, 2p4 total. What is it? 6. All of these elements are having the valence 6. So what will be, this is start from 2, and then 3, and then 4, and then 5, and then 6. Let's talk about TE. If I have TE, which is in the same group like oxygen here, then what will be the last orbital? This is 2, 3, 4, and this must be 5. So this will be 5s2, 5p what?
4.
Hope this is clear also. Is this clear? Good. So now the whole periodic table is based on the electronic structure. You have to be careful with these words. And if you look at the periodic table, look carefully at the periodic table, and you can tell what will be the last orbital for any element from the periodic table. Is this clear?
Doctor, can you repeat the last point?
You can tell now the periodic table. This is the periodic table. The periodic table is based on the electronic structure, which is the S, P, D, and F. Clear? And looking at the periodic table, I can tell what will be the last orbital without doing the structure. As I said, what will be the last 2 orbital of AS? How can you tell? First, what's the total valence of AS?
5.
5. Very good. And what is the last orbital? Look at this one. 2s2p,
D.
3p. So this must be
B.
4s2, 3p. Sorry, 4.
B3.
4p3. See, I already wrote the last orbitals of PE without writing the full structure. Is this clear? Okay, very good.
Yes.
Now the number of d orbitals in the transition metal, you start D1, D2, D3, D4, D5, D6. So if I want the last orbital of Fe, what is it? First, 4s comes before it, so I should say 4s2, 3d what for Fe? 6.
8.
6, because I count. 1, 2, 3, 4, 5, and 6. Okay, next, if I want the structure of rhodium, this one, RH. Now, I should start with what? 5. What? 5 S 2 4 D what? What do you think for D what?
6.
7.
No,
7.
as we said, similar
Five.
to the bubble. Yes, it is 7 exactly. So count. 1, 2, 3, 4, 5, 6, and 7. Is this clear?
انا اتذكر اني حملت لك الانستغرام.
الو يا شباب، سكت السبيكر.
Why it's 7, Doctor? In the periodic table it's written 8.
Your mic, Doctor, is muted.
فتح المايك وعلق مو راضي يقفل.
دكتور المايك مو
دكتور
شغال.
you are muted to answer you.
يا شباب. Okay. Now. Okay, good. All right. So we can tell what's the structure from the periodic table. Next. Next. There are special cases. Special case. And this special case is for chromium and for copper. Chromium is 24. What should be the structure? Let's do it very quickly. What is it? 1:2. Yes?
2:2.
2:2.
2p6.
2p6.
3:2.
3:2.
3p6.
4:2. 3d4. That's the way it should be. But
Doctor, why is 4s2 become before the 3d4?
always according to this structure. Come on. We did this many times. 4s comes before 3d. You have to memorize this. I told you to memorize this very, very well. This table, this structure, memorize it. Is this clear? Very good. Next. So chromium will become like this, but we find that chromium and its group does not follow this structure. It goes 1:2, 2:2, 2p6, 3s2, 3p6, 4s1, 3d5. It becomes is like this, and this is called half-filled, by the way, half-filled structure. Is this clear? Same thing with copper. If I want you to write the structure of copper, which is 29, what is it? It should be 1:2, 2:2, 2p6, 3:2, 3p6, 4:2, 3d9. That's the way copper should be. If we draw it using the structure, if we do it this way, it should be like this. But it's a special case. What is it?
For S1, 3D
D will be full.
4s1, 3d10. Special case. And the same thing with its group, the whole group. Is this clear? And that's the structure of chromium. It should be 4s1, 3d10, like this, the structure. This is special cases only. All right? And last thing we talk about in this chapter, look at, as we said, these are the 2s orbitals. So there are 2 columns here, and this is the 2p. How many columns we should have at this p? How many columns?
6.
6. How many columns in D?
10.
10. And how many columns in F?
14.
Good. Very good. Okay, and with this, we finish the chapter. And then right away, we are already late, we will start chapter 7. So, because chapter 7 is almost continuation of chapter 6, so we're going to continue as is. Still, what's the title of chapter 7?
Electron configuration and the periodic table.
So we are going to talk about the electron configuration, which we already did in chapter 6. Clear? Very good. All right. Now, how the periodic table was developed. The first trial for periodic table considered to be in 1846. Don't worry about even the date, just the beginning. I want to worry about the name, John Newland. John Newland. He came up with a law. I want you to memorize the name Newland, name of the scientist. He came up with law of octave. What's octave means?
ثمانيات.
8. Exactly. A roll of 8. He found that after the 8th element, things become similar to each other. That's all what I wanted to know about Newland. What's the law of Newland? That's the name of the law of Newland. Law of what?
Octave.
Not law of octave. What does that mean? The 8th element is similar to the first one. Clear? I hope clear. Good. Next.
What does it mean, Doctor?
The 8th element is similar to the first one. After the 8th element, things be repeated. Well, that's all what I wanted to know. He noticed that if you look at the element that's known at his time, there is a similarity between, for example, sodium and potassium. And potassium at his time was the, after 8th element, become potassium, and potassium similar to sodium, and he said that this is the law of octave. Every 8th element, the 8th element becomes similar to the first one before it. Is this clear? That's all what I wanted to know, not much. Then what I wanted to know more, there is another scientist, his name is Mendeleev. And I wanted to memorize the name very well, Mendeleev. He did a great contribution to the periodic table. Mendeleev. Okay? As I said, both names are important, but this one is not very important. It's slightly important. And the law is law of octave. All what I wanted to know about Newland is the law of octave. But for Mendeleev, no, I wanted to know more. Okay, at the time of the Mendeleev, the atomic number, what's the atomic number?
Number of protons.
Number of protons.
Number of protons. It's not known at the time of Mendeleev. So it was not there, the atomic number. Okay, so they were putting the elements according to their mass. So they put the element according to their mass. Okay, and Mendeleev did great invention by just looking at the periodic table. I want to tell me one of the great discovery that was done by Mendeleev is at the time of Mendeleev, all right, aluminum, what's under aluminum? Look at the periodic table. What's under aluminum?
GA.
GA at the time of Mendeleev was not known. GA was not known, so at his time it was not there. Okay, and Newland and the others used to put the one which is after it, which is what? GE under it, under aluminum. Look at the periodic table. What comes after GA?
GE.
GE. When Mendeleev came, he said, no, GE cannot be under aluminum. I should put it under what?
SI.
Under, is it SI, which is silicon? Under it is GE. So what did he do? He said, there will be an element that will be discovered later on. We don't know it now, but it will be discovered. And so Mendeleev discovered an element without doing any work. He was just looking at the structure of GE. He said, no, GE is very similar to SI, so I'll put it under SI. And I will keep this place empty when later on scientists discover that there is another element which was not available at the time of Mendeleev. What was this element?
GA.
GA, and they put it. So, as we said, Mendeleev discovered GA without doing any work related to GA. Is this clear? Is this clear?
Yes.
Yes.
Yeah, so it's a great invention without doing any work. Okay, another thing, look at, do you have the periodic table?
Yes.
Okay, look at, as I said, they were putting the elements according to their mass. As the mass, look at the periodic table and look at the mass of the element. You will see as you go across the periodic table, the mass of the element is increasing. But look at the cobalt and nickel. At the time of Mendeleev, tell me what's the mass of nickel?
58.69.
58.69. How about for cobalt?
58.93.
3.93. Which is bigger in mass?
Cobalt.
Cobalt is bigger. So before Mendeleev, the people used to put nickel, and after nickel they put cobalt, because the mass of this one is 58.69, and then this one is 58.93. And as you look at the periodic table, always the mass is increasing. But Mendeleev said, no, no, no. The cobalt belonged to its group, so I put cobalt before nickel. And he put them in this order, and there's another discovery by Mendeleev. Is this clear? These are great discoveries.
Doctor, can you repeat the last point?
As I said, look at, let's look at before nickel. What comes before nickel? Before cobalt? In your periodic table, what's the element before cobalt?
Iron.
Iron.
Iron. What's the mass of iron?
55.85.
55.85. Okay. So look, and what is even before iron? Let's say, let's put one more term. Let me take this away.
Mn.
Iron. What?
Mn.
Mn, manganese. What's the mass?
54.94.
4. So as you go from manganese to iron to nickel to cobalt, look at the mass. What's happening to the mass? 54.94, 55.85, 58.69, 58.93. So nickel should come before cobalt according to the mass, because as you go across, the mass is increasing. Is this clear? When Mendeleev came, he said, no, nickel is similar to palladium and platinum, and cobalt is similar to rhodium and what's under rhodium? I don't know. You have the periodic table. What's under RH?
IR.
IR. All right. So he said cobalt even though it has higher mass, it should come before the nickel in this order. And that's another discovery by Mendeleev, which is good discovery. Okay, good. All right. Now, when we made the arrangement, which element you think will be very similar to chlorine in the periodic table? Chlorine Cl. All the elements in that group should be similar to it. So what's under chlorine?
Br.
What's the other one which is similar to chlorine?
Iodine.
And that's why we'll call all of these, what do we call them together?
Halogens.
Halogens, because they are similar and they have the same structure. Good. Now, as I said in the last lecture, now all these things are according to the structure. The periodic table is arranged according to what?
To electrons.
Yes, to electronic what? Electronic structure. This is clear. Very good. And that's why we know. I want now to tell me what's the meaning of valence electron? Valence electron, what does it mean? Is actually number of n, I mean s, number of electrons in the last S and P. Is this clear? Okay, now I want to tell you, now the valence electron are actually what's written in here. You should know what's the valence electron of this group. What? 1. What's the valence electron for this group? 2. What's the valence electron for this group? 3. What's the valence electron for this group? 4, 5, 6, 7, and 8. I want you remember these numbers. You don't have to memorize it. You have to know it. Look at your periodic table and just write whatever I wrote here. 1, 2, 3, 4, 5, 6, 7, and 8 in the periodic table. And whatever I write here in the red is the valence electrons. Valence electron. So, and it's for the same group. What's the valence electron for Br? What's the valence of Br? What's the valence of Br? Yes? 7. Okay, what's the valence for Sn?
4.
Exactly. What's the valence for P?
5.
5.
5. What's the valence for xenon?
8.
What's the valence for aluminum?
3.
3.
3. What's the valence for Sr?
2.
2. The valence of K?
1.
1. Exactly. 1 and 2, 3, 4, 5, 6, 7. And you can tell what's the number. What's the valence of argon?
8.
Exactly. Oxygen?
6.
Silicon?
4.
4. Boron?
3.
3. Okay. CS?
1.
1. Ra?
2.
That's all. And the valence electron are the last S and P. If you look at the structure of the valence of CS, the last step for CS, for example, it is 6S1. Only one, and that's it. If you look at the structure of carbon, for example, what is it? 1s2, 2s2, 2p2. How many electrons do you have in the last S and P? How many electrons?
4.
4. I already told you this, it's available here. Is this clear? Okay. If I want to write the structure of phosphorus, what's the structure of phosphorus? 1s2, 2s2, 2p6, 3s2, 3p1. What's from the structure? What's the last? How many electrons do you have in the last S and P? Oh, sorry, this is wrong. Yes, no. Yes. How many electrons do you have? And this is the structure of phosphorus. How many electrons do we have in the last S and P?
5.
5. What's the valence of phosphorus?
5.
5. I already, you know the valence before you even write the structure. Is this clear? So, yes. So the valence is the last SMP. Last SMP is you have to. This you have to read at home. What's the meaning of metals? We know where are the metals and the non-metals and the metalloids. Okay, non-metals, I mean the metals, if you have the periodic table, where are the metals? Do you know where are the metals? This is this metal, so okay, even this one, okay. Now, what did I wrote here? Look at the line. Whatever under whatever under this line is considered to be what? What are these?
Metal.
Metals. Whatever above this side, what's this?
Non-metals.
Non-metals. Whatever around the line is called what?
Metalloid.
Metalloids. You have to memorize these names. Okay? You have to know this. Now we're going, and the property, you go ahead and read them. I don't want to talk about them, but these are the metals, these are the non-metal, and the non-metal exists as H2, N2. We already talked about this before. O2, F2, Cl2, Br2, I2, and P4. Sulfur is existing as S8, but we are going to deal with it as S, not as S8 in our structure. You have to read this.
All the non-metals, Doctor.
What?
All the non-metals.
No, this is not the whole non-metal, part of the non-metal. But these are non-metals, and this is the structure. We have also noble gases. Are these metals or non-metals?
Non-metals.
They are non-metals. You have to know this, and also you have to know the structure is like this. Okay, and the metalloids, these are the metalloids, and you have to know them from the structure. The metalloids that I show you in the periodic table. Okay, good. Now, let's go to the another subject here, which is called effective nuclear charge. Hello? Effective nuclear charge. Now, what is Z? When we have any element, like for example, sodium Na, we write, what do we write here? What's the letter that we put here?
Z.
And here? at the top?
A.
A. What is Z?
Atomic number.
Atomic number. Okay, what is A?
Mass number.
Mass number, exactly. Mass number. Very good. Now I'm going to talk about another thing which is called effective nuclear charge. Effective nuclear charge. The atomic number is the nuclear charge, right? So if I have, for example, hydrogen 1 and 1, what's the nuclear charge? What's the charge on the nucleus?
1.
1. If I have sodium, which is 11, what's the nuclear charge? Sodium.
11.
11 plus 11. Okay. If I have like K, which is 19, what's the electronic charge for nucleus charge for calcium?
Plus 19.
Is it clear? Now Z is the nuclear charge. I want to introduce something else, which is effective nuclear charge, and I will put it Z with a star, like something like this. I will call this nuclear charge. What do I mean by this? If I have sodium, how many electrons do you have? How many? What's the nuclear charge of sodium?
11.
11. 11, exactly. Let's draw the structure of sodium. 1 is 2.
2 is 2.
1 is 2. 2p
2p6.
6.
3 is 1.
1. All right. Now, I want you to imagine we have 11 proton here, 11 proton, and we have electron here, and we have 2 electrons here actually, and we have 2 electrons here. Which one will be attracted stronger to the sodium? Is it the first 2 or in here 1 or in 2?
1.
In 1 stronger. Why?
Closer to it.
Closer, exactly. Not only that, also these are shielding these electrons. What's the meaning of shielding? Or screening. كأنه يغطي، يعني shielding. shield هو الدرع اللي الإنسان يلبسه، يسمونه الشيلد. تعرفون لما في الحروب أول لما كان سيوف وكانوا يلبسون shield. Shield, this means to protect themselves from the من السيوف يعني. shield اللي هو يحطوه على الصدر، اللي هو الحماية، غطاء أو حماية. Alright? These electrons are shielding these electrons from seeing the nucleus. How about this one? How many electrons? The last electron here. All these electrons will shield this electron from the nucleus. Is this clear? So, what will be the power of the nucleus to 1s2? Maybe it is 11. What will be the power for 2s2? Maybe it become what? 9 or even less than 9. Is this clear? What will be the power of sodium and the 2p?
Even less.
Even less, maybe 7 or 6, let's say. What will be the power for 3s1? It will be maybe 2. Is this clear? This is called Z effective. So define what's Z effective. The effect of Z in the last electrons in the last sp electrons. The nucleus, the effect of nucleus, on last sp electrons. And as I said here, what's the power of sodium on the first two electrons? Maybe 11, as is, around that. Okay, how about the effect on the last and the 2s? It will be maybe 9. Why? Because they are further away, and also because these electrons are doing what? Shielding or screening. Is this clear? Okay, how about these electrons? Maybe the power of the nucleus will be only 6. Why? Because again, these electrons are shielding and it's further away. How about the last one? Will be very far away, and all these electrons are shielding. That's why this will probably see the power only 2, not 11, but 2 only. This is called Z effective. Is this clear? Okay, this is called Z effective nuclear charge. The effective nuclear charge. And the shielding, this shielding, which we did here, we will give it sigma structure to represent it. Sigma. All right. So what is, from the numbers that I gave you here, what is the shielding of 1s2 to the 1s2 to 2s2? What's the shielding? What's the sigma equal to? Maybe 2, according to what I wrote here. Is this clear? I hope it's clear. Good. Now, this is called Z effective, as I said. What is Z effective? What is Z, by the way? What's this equation? What's Z?
Atomic.
Atomic what?
Number.
Atomic what?
Number.
Number. Exactly. What is sigma?
Shielding number.
Shielding, not number. Shielding, yes, number. It is number, but it's actually shielding. Shielding. What is Z effective?
Efficiency of
effective nuclear charge. Because atomic number is nuclear charge. Same word. And this is effective nuclear charge. Is this clear? Don't memorize any number. I want you only to memorize the equation. But the numbers, don't memorize any number other than Z. Of course, everybody knows what is Z for any element. Okay, so the effective nuclear charge has the meaning felt by valence electrons. How the valence electron, what's the meaning of valence electron? What's the meaning of valence electron?
Last electron.
Last. No, what last? Which last? Which electrons? What's the meaning of valence electrons?
Last sp electrons.
Last sp electron. And as you can see here, this is the nuclear charge, which is, you should know this one. 3, 4, 5, 6, 7, 8, and 9. But the last sp electrons, look at the numbers here, it feels it, it's not 3 for it because of the shielding, it feels only 1.28. This one 1.91, this one 2.42. I don't want you to memorize this number. Don't memorize this number, but I want you to notice what is happening to the effective nuclear charge as you go from here to here.
It's increasing.
Increasing. So because of this because it is increasing. What will happen to the size of the atom? If lithium is this big, if you go to Be, the effective nuclear charge is stronger. So what will happen to the size of Be? If this is lithium, what will happen to the Be? Be will be what?
Less in size.
Smaller than lithium, because there is more effect in the nucleus than this one. Is this clear? How about if you go to B? It will be even less. How about if we go to carbon? It will be even less. And that's why you will find the size is even decreasing and decreasing until it becomes like this. And that's exactly what happened to the size. Because of the effective nuclear charge, look at the size here. As you go across, what happened to the size of the atoms, of the elements? What happened? Hello?
Decreasing.
Decrease.
Why is it decreasing? Tell me why it is decreasing like this.
Because the effective number is increasing.
The effective is increasing, exactly. Okay, is this clear? Very good. So I want you to know all of these things. We already finished this thing. And as I said, don't memorize these numbers. Don't worry about this number. What you should know only, as you go across in the periodic table, what's happening to the effective nuclear charge?
Increasing.
Increasing. That's all what I want you to memorize in here. Okay? All right. With this, I will stop here. And before we leave, we will take the attendance as usual.